All right, strap yourselves in, because today we're diving headfirst into some of the biggest mysteries the universe has to offer. The kind of stuff that keeps astrophysicists up at night, you know?
Oh, yeah.
We're talking gravity, dark energy, and those crazy tiny particles, neutrinos.
It's going to be a wild ride.
You ready to bend your mind a little?
Always up for a good mind-bending session.
Perfect. So you sent me this article titled Neutrinos, Dark Energy, and Einstein. DII maps the universe's secrets.
Right.
And I gotta be honest, even for someone who geeks out on this stuff, this article is packed.
It is dense, but that's because it covers so much groundbreaking research. The heart of it is about a project called DII, the Dark Energy Spectroscopic Instrument,
Okay.
and how it's literally changing how we understand the universe, you know?
I'm already intrigued. Go on.
Well, did you know that there are over 900 scientists working on this?
900. That's an army of scientists.
I know, right? It's a massive collaboration. And they're using this amazing telescope that can capture light from, like, 5,000 galaxies at once.
Wait, hold on. 5,000 galaxies at the same time?
Simultaneously. Can you imagine the data they're pulling in?
Okay. My mind is officially blown.
Just wait. There's more.
So, where do we even begin with all this? What are the big, holy cow moments from this DSI project?
Well, one of the biggest things is that DSI is actually confirming Einstein's theory of general relativity, but on a cosmic scale.
Whoa, hold up.
Yeah.
It's amazing that a theory from a century ago still holds up when we're talking about millions of galaxies.
It's incredible.
But isn't general relativity all about gravity?
Well, yeah.
How does DSI, which is focused on dark energy, actually confirm that?
It's all about how DSI maps the universe. Remember those baryon acoustic oscillations, or BAOs?
Oh, yeah, those ripples in the early universe, right?
Exactly. They're like the universe's baby pictures. And what's fascinating is that the science of these BAOs is directly tied to how fast the universe was expanding at different points in time. DSI is measuring these BAOs at various distances, so they can basically track that expansion rate throughout history.
Okay, I'm starting to see the connection. So by studying these BAOs, they're essentially tracing the influence of dark energy, and that somehow links back to general relativity.
Exactly. See, Einstein's theory predicted that the presence of matter and energy would warp space-time, and that would affect things like the path of light and the expansion of the universe. By mapping these BAOs and seeing how they've evolved over billions of years, DSI is actually testing Einstein's predictions about the relationship between gravity, space-time, and the expansion of the universe.
That's wild. So even though DSI is focused on dark energy, it's giving us clues about gravity itself. It's all connected.
It really is. It's like this intricate web. But here's where things get really interesting. DSI's data is hinting that dark energy may not be as constant as we once thought.
Wait, what?
Yeah.
You mean dark energy, the mysterious force that makes up most of the universe, could be changing?
It's a radical idea, right?
Mm-hmm.
For the longest time, we assumed dark energy was constant, this unchanging force pushing the universe's expansion. But what if it's not? What if it's evolving, getting stronger or weaker over time?
Okay. My mind is officially rebelling.
I know it's a lot to take in.
So what in DRI's data is suggesting this? Are we talking glitches in the system or something?
Not glitches, but anomalies. When they look at the BAO patterns at different distances, some of them don't quite line up with a universe where dark energy is constant. It's like they're finding wrinkles in the fabric of space-time.
Wrinkles?
Yeah, like little inconsistencies.
Okay, so how do we make sense of these wrinkles? Does this mean everything we thought we knew about dark energy is wrong?
Well, it's too early to say for sure, but if these anomalies are confirmed by further research, then it could drastically change how we understand the universe. We might have to totally rethink our cosmological models and face some pretty mind-bending possibilities.
Okay, I am so hooked right now.
I told you.
But before we go too far down this rabbit hole of evolving dark energy, this article also mentioned neutrinos. Where did those little guys fit into all of this?
Neutrinos. The tiny rebels of the universe. They're so small and interact so weakly that they zip through practically everything, barely leaving a trace.
Like little cosmic ghosts.
I like that, cosmic ghosts. But yeah, they're notoriously hard to study.
So how is DSI helping us learn more about them?
DSI is indirectly probing neutrinos by looking at how they affect the large-scale structure of the universe. Remember we talked about how BOs and gravity are connected?
Right, the BAOs are basically a historical record of the universe's expansion.
Exactly. And even though neutrinos are incredibly tiny, they still have mass. However small, that mass still exerts a gravitational pull.
Wait, are you telling me that something as small as a neutrino can affect the universe's structure?
Believe it or not, yes. It's like a tiny pebble making a ripple in a pond. On a cosmic scale, it's enough to influence how matter clumps together and forms galaxies. And that's where DESI steps in. By studying those BAO patterns in detail, they can actually infer the total mass of neutrinos in the universe.
So DSI is like a giant cosmic scale weighing these elusive particles. That's just
Mind-blowing.
seriously mind-blowing. But even if we figure out the mass of neutrinos, they're still incredibly mysterious. Why is knowing their weight so important?
It gets to the core of particle physics and our understanding of the forces controlling the universe. You see, in the standard model of particle physics, our best model of the universe's building blocks, neutrinos, were first thought to be massless.
So the fact that DO have mass, however small, kind of messes with that whole model.
Exactly. It hints at something beyond the standard model, some new physics we haven't figured out yet.
Yep.
By accurately measuring the neutrino mass, DESI is giving us clues to what that new physics might be.
It's like neutrinos are holding the key to a whole new level of understanding about the universe.
And who knows what other secrets they're holding,
This is incredible.
isn't it?
Okay, I need to take a breath for a sec. But before we fall deeper into particle physics, I'm curious about the people behind all of this. You mentioned over 900 scientists are involved with DSI.
It's a huge team.
What's it like to have so many minds working on a single project?
It's a true testament to global collaboration. You've got experts from every corner of the planet, each bringing their own unique expertise to the table. It's like an orchestra, with everyone playing their part to create something amazing.
I love that analogy. It captures the beauty of working together in science.
And one of the coolest things about DSI is that it's not just about mapping the universe in 3D, it's about using that map to unravel the biggest mysteries in cosmology, like dark energy and the role of neutrinos in the universe's evolution.
We've been handed this giant puzzle, and DSI is helping us put it together piece by piece.
That's a great way to put it. Each galaxy, every measurement, brings us closer to the bigger picture.
I can't wait to see what else they've discovered.
Me neither. But let's take a quick pause here. When we come back, we'll delve into how DESI is changing what we know about the universe's past, present, and maybe even its future.
All right, sounds good. All right, we're back. Ready to go even deeper into the world of DESI and those cosmic mysteries we were talking about.
Buckle up.
We left off with those BAO anomalies and the possibility of, evolving dark energy. It's amazing to me that DESI is using those ancient sound waves to probe such crazy concepts.
It really is revolutionary, and we've only just begun to explore what DESI is capable of.
Oh, there's more.
So much more. What really gets me excited is how DESI is pushing the boundaries of what we can measure in the universe.
Okay, I'm all ears.
So think about it. We're trying to study something as elusive as dark energy, this force that doesn't interact with light in a way that we can see.
Right.
The only way we even know it exists is because of its effect on the expansion of the universe, you know?
It's like trying to study a ghost. You can't see it directly, but you see what it does.
Perfect analogy. And that's where DESI's precision comes in. By mapping millions of galaxies in 3D and analyzing those BAO patterns in such detail, they can track the universe's expansion with an accuracy we've never had before.
So it's not just about mapping the galaxies themselves, it's about measuring the spaces between them.
Yeah.
How those spaces have changed over billions of years. It's like cosmic cartography on a whole other level.
It is. And it's that level of precision that allows them to see those tiny anomalies in the BAO patterns. The ones that suggest dark energy might not be constant after all.
I'm still trying to wrap my head around the idea of evolving dark energy. I mean, if it's true, that totally changes the story of how the universe evolved, right?
Yeah, it has mind-blowing implications.
Yeah.
It means the force pushing the universe apart isn't steady and unchanging,
Right?
but something way more dynamic. Something that could even change the ultimate fate of the universe as we know it.
Whoa, okay, now we're getting to the big questions.
I know, right?
What are some of the scenarios if dark energy really is evolving? Like, could the universe end differently than we thought?
It definitely could. For a long time, we thought the universe would just keep expanding forever, eventually fading into this cold, dark void. But if dark energy is evolving, that all goes out the window.
Okay, so what are the other options? What could happen instead of just fading away?
Well, one possibility is that dark energy keeps getting stronger over time, which would speed up the expansion of the universe and eventually tear everything apart, galaxies, stars, even atoms themselves.
That's terrifying.
It's called a Big Rip. Pretty dramatic ending for the universe, don't you think?
Intense. But are there any other options? Something a little less apocalyptic.
Of course. Another scenario is that dark energy weakens eventually, or even reverses course, causing the universe to slow down its expansion and collapse back in on itself.
So instead of expanding forever, everything just comes crashing back together.
Yeah, it's called the Big Crunch, essentially the opposite of the Big Bang.
Wild. So with evolving dark energy, we basically have no idea how the universe will end.
There's also the chance that dark energy fluctuates. So you'd have periods of expansion and then contraction, almost like the universe is breathing.
My mind is officially blown. It seems like with evolving dark energy, anything is possible when it comes to the fate of the universe. It's both kind of terrifying and exciting at the same time.
It is. It's like we've stepped into a whole new world of possibilities, and we're just starting to understand what it all means.
So how do we even begin to figure out which of these scenarios is most likely? Is it just a matter of waiting for more data from DDI?
That's a big part of it. DI is still in its prime data gathering phase. As they map more and more galaxies and get even more precise with their measurements, we'll have a much clearer picture of how dark energy is behaving.
But what if, even with more data, we still have unanswered questions about dark energy? I mean, it's pretty mysterious.
Oh, absolutely. It's crucial to remember that we're dealing with something we fundamentally don't understand. Dark energy makes up about 70% of the universe, and we have no clue what it is.
Just like a giant puzzle where most of the pieces are missing. What about the other pieces? Are there other projects or research going on that could help us understand dark energy better?
Absolutely. There are many brilliant scientists tackling this problem from all sorts of angles. Some are exploring new theories of gravity, while others are trying to take dark energy directly in a lab. It's truly an exciting time for cosmology, with new ideas popping up all the time.
Maybe someday we'll have that aha moment where it all clicks into place and we finally get what dark energy truly is.
That's what we're all hoping for.
Speaking of those fundamental truths, I want to go back to neutrinos for a minute. We talked about how DESI is helping to measure their mass.
Yeah.
But to be honest, I'm still not totally clear on why that's such a big deal. Can you remind me why those little particles are so important?
Sure. So neutrinos are some of the most abundant particles in the universe. They're created in stars, in supernovae, even in nuclear reactions happening inside us right now.
Wait, what? Neutrinos are inside us.
Billions of them are passing through you every second. But they interact so weakly that they don't really affect us.
That's both amazing and a little creepy. But okay, back to my question. Why is figuring out their mass so important?
Because it tells us something about the nature of matter itself. You see, in the standard model of particle physics, which is our best theory about the universe's building blocks, neutrinos were originally thought to be massless.
So finding out that they actually have mass, no matter how small, that kind of throws a wrench in things.
Exactly. It suggests there's something beyond the standard model, some new physics we don't yet understand. By measuring the neutrino mass, DSII is giving us clues about what that new physics might be.
It's like neutrinos hold the secret to a whole new level of understanding about how the universe works.
That's a great way to put it. Tiny particles, big implications. And who knows what other secrets they might hold. For example, some physicists think that neutrinos could be their own antiparticles.
Really?
Yeah, which would totally change how we think about the early universe and the nature of matter and antimatter.
Okay, my mind is officially blown again. The more we learn about neutrinos, the more questions come up. It's like this never-ending journey of discovery.
Exactly. And that's the beauty of science. It's a constant process of questioning, exploring, and refining what we know about the world around us. And projects like DSI, with their incredible scope and precision, are pushing the boundaries of what's possible, allowing us to glimpse realms we never thought we could explore.
It makes you wonder what other mysteries are out there just waiting to be uncovered.
That's the exciting part. There's still so much more to discover, so many questions left unanswered. And with each new discovery, we're getting closer to understanding our universe and our place within it.
This has been such an incredible journey. I'm really excited to hear more about what DSI has found, what other insights are hidden in all that data.
Well, before we get into specifics, I think it's worth taking a step back and appreciating the sheer scale of this project.
You're right.
And what it represents for scientific collaboration.
We've been so focused on the mind-blowing discoveries that we haven't really talked about the people behind it all.
Exactly. The human story is just as fascinating as the scientific one.
Yeah, we've been knee-deep in evolving dark energy, neutrinos, and how DSI is changing the game in cosmology. But you're right, we haven't talked much about the people behind it all.
It's easy to get caught up in the data and the discoveries.
Totally. So tell me, what's it like having over 900 scientists from 70 different institutions working together on one project. That's got to be insane.
It really is. Imagine this massive, virtual lab spanning continents with teams working day and night, sharing data, insights, ideas. There's this amazing sense of community, this shared drive to push the boundaries of what we know, even if it means challenging everything we thought we understood.
It's kind of inspiring to think about all those brilliant minds coming together like that, not for personal gain, but to achieve something bigger than themselves.
It really captures the true spirit of science, and the collaboration goes beyond just data collection. These scientists are constantly discussing and debating, refining their understanding of the universe together.
Working together to put the pieces of the puzzle together.
Exactly. And this open collaborative approach is becoming so important in science. The challenges we face today, from understanding dark energy to things like climate change, they demand global cooperation and a willingness to share knowledge.
It makes you wonder what we could accomplish if we could apply that same level of collaboration to other areas.
It's exciting to think about. But we can't forget about the technology that makes all of this possible. DESI itself is a testament to human ingenuity.
I mean, a telescope that can capture light from 5,000 galaxies at once. That's mind-blowing. Splitting that light into different colors to reveal the secrets hidden within.
It's like we've been given this superpower, the ability to look back in time and unlock the mysteries of the cosmos. And the fact that we created the machine to do that, that's awe-inspiring.
The data they're collecting must be incredible.
It's a goldmine of information, not just about dark energy and neutrinos, but about the formation of galaxies, the distribution of matter, so much more.
It's like they've given us a new set of eyes to see the universe with.
And they're only just scratching the surface. Who knows what other secrets are hiding in that data, waiting to be uncovered?
It's like opening a door to a whole new world of understanding, a world we're only beginning to explore.
Absolutely. And this is just one project among many. All over the world, scientists are pushing the boundaries of knowledge, building bigger telescopes, developing new theories.
Right?
It really feels like a golden age of discovery.
It does. It really does. It's a time when the universe is slowly revealing its secrets to us, thanks to our curiosity and the incredible tools we're developing.
It's a reminder that even with so much we don't know, the human drive to explore and understand persists. That desire to unravel the mysteries of the universe is a core part of who we are.
And that journey, with all its ups and downs, the moments of awe and wonder, that's what makes it all worthwhile.
Well said. If you're listening and feeling inspired, remember that you too can be a part of this journey. Keep asking questions, keep learning, and never stop looking up at the stars in amazement.
Because who knows what incredible discoveries are still waiting out there for us. Keep those minds curious, keep your hearts open to wonder, and keep diving deep into those mysteries all around you. Until next time, happy exploring.